And hello, welcome back everybody to our OpenFOAM little discussion. So in today's video, we want to talk about relaxation factors, and we were talking previously about the piezo loop and the inner and outer loops. Okay, inner and outer loops, and we are saying that if we have the inner loops more than one time and the outer loop one time, that is the piezo loop. Pimple loop is where we have more than one outer loop. Okay, let me get the right color scheme. Yeah, more than one outer loop, but only one time of more than one outer loop, and of course you can have more than one inner loop. But as long as the outer loop has more than one time, that is being used more than one time, i.e. this red box has been repeated more than once, then we can call it a pimple algorithm. So it won't always be the case where the pimple algorithm gives you the result you want. For example, in this case C1, where the n outer characters is 2, we have a diverging kind of a solution where you don't actually have convergence and the residuals are still pretty big. Residuals means the difference between the nth solution. That means if your velocity or whatever field is here, and your next iteration is always like some distance apart, and this will be called the residual. Of course, it means that if you have your nth guess being a certain number and the n plus 1 guess being relatively close, meaning you say you have a small residual, you can say you more or less have converged if your residual is small. So if you guess between the nth iteration and the nth plus 1 iteration, if it's very far apart, it means that after many iterations it's very far apart. That means it has not converged, or it's a diverging kind of a case. If it's a small residual, as you can see, if your nth guess is this and your n plus 1th guess is what I just clicked here, then you will have a you can say your solution is more or less converge. I hope you are familiar with this. Should have been elaborated in the last few videos. But anyway, just take note that we will need to use this concept of residuals very often, and we generally want residuals to be very small, and I'll explain the concept of residual a few more times so that hopefully it gets more clear as we go along. So the thing we want to another tool we can use to make these residuals smaller is something called a relaxation factor. It's something I wanted to talk about in the last video, but I kind of ran out of time. And what is actually this thing called the relaxation factor, you might ask? So, okay, for example, let's say we have a case of a 3 system of equations. So, alright. So we'll use a very simple example first. So let's say example of Gauss-Seidel iterations. I hope you know what Gauss-Seidel is. I am not going to explain here. It's just a numerical method, and I'm not going to say how the thing is derived or what. I'm just going to use it here because anyway, this is what some OpenFOAM schemes are using. They are using Gauss-Seidel a lot. So okay, we have a system of 3 equations. So let's say let's give you 5x plus 2y plus 3z equals to 10. Let's give you another random one, minus 6x plus 10y plus z equals to 13. And I'll give a small number, x minus 2y plus 1, or maybe I'll give 5z equals to, or maybe I give you, yeah, maybe x plus 2y. All right, or maybe I'll give you 5y plus 2z. Just some random numbers equals to 6. Okay, so I hope I'm not typing the same equation. This should have a unique solution. Should have a unique solution of what? Yeah, it should have a unique solution of x, y, and z being a certain value. Of course, to start solving this thing, we kind of want to rearrange this. Okay, we rearrange x as follows. Is from the first equation. From the first equation here, we can rearrange x as follows. X equals to 1/5 times 10 minus 2y minus 3z. So I'm just bringing all of that to the other side. Yeah, and that will be equal to 2 minus 2 over 5, which is 2 over 5y minus 3 over 5z. All right, so what I do is just bring the 10 over. I'll just make x the subject here. As for this, okay, if you're familiar with the concept of diagonal dominance, well, I can explain it a little bit here. Okay, if you're not familiar with it, I can explain it a little bit, in just a little while. Okay, so anyway, so this is your first equation of x. Okay, so the standard Gauss-Seidel is as such. We can do the same for the y and z. So for the y, we can do this as follows. Y equals to 1/10 times, okay, 13 plus 6x minus z. Okay, so it's 15 over 10 is 1.5 minus 0.6 minus 0.1z. Okay, so the y is as follows. So 0.6x. Okay, I'll just copy and paste this whole thing here. And of course, if I can do the same for z, z equals to minus 6 plus 5y minus x. So I subtract add 5y to both sides, subtract x from both sides, then times minus 1. You'll get z equals to, okay, minus 6 minus 5y, okay, minus 6 and minus 5y, and the last one is plus x, right? So x minus 5y minus 6, that will give you z. So this will be our system of equations we want to use to kind of guess. Okay. Okay, I think, alright, I needed to, I have these 3 equations. Okay, so this is what we want to start with. Now, normally, okay, let's say we start with 0, 0, 0 as our initial guess. Means the initial guess of x equals to 0. Okay, x, the 0th guess, equals to 0. Y, the 0th guess, equals to 0. Z, the 0th guess, equals to 0. This is our initial guess. Okay, we always need to have an initial guess in a numeric system of equations. So let's say I'm not going to actually iterate out this system, but I want you to see a few patterns here. normally we like to do this thing called diagonal dominance for our system of equations here. Means to say, if we are using this equation for x, this coefficient of x should be the biggest. If we are using this equation for y, the coefficient of y here is the biggest. If we are using this equation of z, the coefficient of z here is the biggest. So let me highlight those up for you to say why is it called diagonal dominance. So normally, if you have studied numerical solutions before, let me try again. Try and highlight the 5x without highlighting everything else. So yes, normally we want the coefficient on these highlighted terms to be the biggest, right? Because that supposedly gives us the biggest stability. So normally the right way is to have a very large coefficient of z. Unfortunately here, the coefficient of z doesn't really matter. Okay, doesn't really matter here. So the only way is to say, okay, this is, let's say you have a 10 over here, then you have this thing called diagonal dominance because the coefficients on these diagonals are the biggest. So that, okay, that's ideal anyway. Why do we want this diagonal dominance? So that when we rearrange the equations here, we will have a coefficient of less than 1 over here, over here, over here, and over here. Okay, you see what I just highlighted is the coefficients of y and z. When we say x equals to something of this fashion, all the coefficients here should be less than 1. That is going to help in our stability. Why? So let's take up paint, like a new section here. Okay. So why do we want diagonal dominance? Let's just do a little bit of experimentation here, right? So I'm gonna get this over here. Yep, I'm gonna copy and paste, and let's put it in paint. And so I would like to just color this this part black first, so it will look nicer. Okay, wonder what happened there. But okay, I'll just get rid of this. I'll use a light blue. Okay, so we were talking about making those coefficients less than 1, and let's say we started with oopsie, just ignore that. We start with an initial guess of 0, 0, 0, 0, 0, 0. So just bear with me and stay with me. We have initial x 0 equals to 0, y 0 also equals to 0, and z of 0 equals to 0. But these are the initial guesses. Now obviously, between this and the true value of x, okay, sorry, that should be y. The true value of y and z, true value of z, okay, there'll be, okay, there'll obviously be some error, right? There's a error of x, this is the error of y, and this is the error of z. Okay, and yeah, and every time, let's say you have your first 0th iteration, I mean the hope is that as you keep substituting, you get closer and closer to the true value of x. So let's say from x0 to x1, you have one iteration. You hopefully you have your x, y, and z, of course. X, y, and z first iteration. Hopefully you're reaching closer and closer to the true value of x, y, and z with each iteration. So let's say you converge after 10 times. And how is convergence usually determined? So convergence is usually determined when the residuals reach below a certain point. So what are residuals? Residuals are like the difference, let's say between, let's say your iteration 11. So example, your iteration 11, the residual will be your iteration 11 minus the value of the 10th iteration. So let's say between your 11th and 10th iteration, if the difference is small, if this difference is small, then I would also say that this difference is called the residual. So this residual we assume is small, and if it's small enough, we can say that this equation is converged and you're more or less near the true value of x, y, and z, or in this case we're just looking at the x, right? So this is the basic idea of the Gauss-Seidel kind of iterations. All right, but of course with each of these iterations, they will always contain some error, right? They'll always contain some error between this iteration and the true one. And likewise between this, let's say the 11th iteration, the 10th iteration, there will always be some residual. And the reason why you want to have a very good set of equations with all these coefficients less than 1 is that you don't want your residuals to grow. And the reason why these residuals grow is because, let's go one equation at a time. So x equals to, let's say 2 minus 2 over 5y minus 3 over 5z. Okay, 2 minus 2 over 5y minus 3 over 5z. Okay, so 2 minus 2 over 5y minus 3 over 5z, and then you substitute, y equals 0 here. Okay, your zeroth guess of y. Okay, and your zeroth guess of z, z0, right? Your zeroth guess of y and z will be substituted here, and obviously it will have some error associated. And what happens to this error? It will be multiplied by this coefficient, 2 over 5, 3 over 5. So in effect, the effect of this error gets The effect of this error gets multiplied by 2 over 5 and it becomes smaller. And likewise, if you were to do the same for the y equation, right? You have the x error being multiplied by 0.6 times, the z error, even better, multiplied by 0.1 times. All well and good. The only problem is that you look at the z equation, the last one. If you have an error in y here, right? You have an error in y here. So you have this said error in y over here. Let's say you have an error in y, and then you have some error in x, right? So x error is going to be multiplied by 1 time. So that's well and good. That's fine, tolerable. But this error in y is going to be multiplied 5 times. So error in y is multiplied 5 times in this value of z when you guess your next value of z. So great. That's going to give you some problems. Nevertheless, it is pretty good because when you substitute this value of z back here as per your Gauss-Seidel iterations, it's going to be dampened. So the error is going to be multiplied by 3.5 times. Okay, so likewise, this value of y is going to be substituted here, and that's going to be multiplied 2.5 times. So this will become your next value of x, and by the time you put this x here, the error associated with this z is going to be multiplied by 0.6 times. So I mean, the hope is that overall it's going to be a very stable system, because the effect of the error overall is being damped, meaning to say that the error is not exponentially increasing with each iteration. So hopefully, you know, this is what the importance of diagonal dominance is about, and ideally we want to have all our equations like that. Unfortunately, in most life scenarios, you cannot 100% guarantee yourself to have this kind of diagonally dominant equations where your error is always getting damped. So let's say I just change this system of equations. I will change it to let's say, instead of me having 2 over 5y, I have 20y instead. 3 over 5z, I have 50z instead. Okay, and instead of the second equation, the coefficients being 0.6x and 0.1z, or minus 0.6x minus 0.1z, I mean the sign doesn't matter, it's the magnitude that matters here. Instead of that, I have 5x and 7z. So if I have something like this, what's going to happen? Okay, what's going to happen? Okay, so what's going to happen is that I'm going to try to have my equation as such. So let's say we start with y and z here. Remember, we have some error, and this error is going to be multiplied 50 times for z. The z error in z is going to be multiplied 50 times. Error in y is going to be multiplied 20 times. Then you're going to use this to guess your new value of x. So x new, or x calculated, you will have 50 times error of z and 20 times error of x, which is a little too much. And likewise, when you substitute this value of x in here, all of this is going to be multiplied 5 times. Alright, so 5 times error, 5 times the error of x. Okay, so 20 times, oh, this one should be y, sorry, this one should be y. 5 times the error of x will be that. Yeah, so when you put this here, the error multiplies by 5 times, and the error of z multiplies by 7 times error of z. So that becomes your y calculated value of y, right? So it becomes like this. Then you put this here, all of this will be multiplied 5 times error of y in your last equation, plus 1 times error, 1 times error of x. So that will become the z calculation. You can see that once we substitute this z back here, this error will be multiplied again by 50 times. So that's the weakness of this. Now, how are we going to solve this problem? So we have this thing called a relaxation factor, which was the whole point of these few videos. I want to explain to you what relaxation factors are about. Relaxation factor. You may see people use the symbol lambda, you can use the symbol omega, you can even use the symbol phi. Whatever it is, maybe not phi, maybe alpha. Whatever, doesn't really matter. Okay, so what are the relaxation factors? Okay, so when you pay attention to the x, y, and z calcs here, and we notice that the equations here are so-called, the coefficient of these y and z, for example, x and z here, these are all greater than 1. How can it be, or how are we going to make it such that all these factors are now less than 1? So let's say you want your new value of x equals to Well, I will give you some factor. We'll call it, okay, omega, for example. Omega will be multiplied into, let's say, okay, 2 minus 20y minus 50z. All right, 2 minus 20y minus 50z. Okay, and you want to make this less than 1, for example. So let's say omega becomes 1 over 100. Okay, if I make omega 1 over 100, okay, what can that do for us? So this will be multiplied into 20, and then this will become 0.2, which makes the y stable, and this can be multiplied into 50 to make it 0.5 to make the z error stable. But of course, if we just multiply this by 1 over 100, your x value will be diminished by that much. So to balance it off, what they do is okay, you find this actually being a sort of weighting factor. We have 1 minus omega, and omega, if it's used to control iterations like this, okay, omega between 0 and 1. Okay, this effectively makes the coefficients less smaller, and it stabilizes the equation. And then we have 1 minus omega into x old here. All right, yeah, what happens is that, okay, this 1 minus omega, because omega in this case is 1 over 100, this will be 0.99 x old. So now you see that, hey, the idea is that I am using a weighting factor, which is this. I'm using a weighting factor, and I'm making the rate at which x new kind of changes from x old. I'm slowing this down, slowing the change, slowing delta, the change. So this is called under relaxation. All right, relaxation. Okay, so I'm going to continue my discussion in the next video, but I want you, okay, to know, okay, this resource is very helpful. It's called Mathematics, Numerics and Derivations in OpenFOAM. It's by this guy called Tobias Holzmann from Holzmann CFD. He's very good guide, and I get a lot of the stuff from there. Okay, so I'll leave this in the link, yeah, and then you can go and check it out yourself. But long and short, okay, relaxation factor is here, and it's needed if you have a very bad system of equations. Okay, so this one, I'll go through this in the next video. I think there's some error down there, but just ignore this. I'll go through that in the next video. Relaxation factor is needed if you have a bad system of equations. I need to say the error multiplies with every guess. So what this is called is under relaxation. Okay, under relaxation. Over relaxation does the opposite, but again, that kind of I can discuss in the next video. Okay, see you next time. Bye bye.